A vector space is a mathematical structure formed by a collection of elements called vectors, which may be added together and multiplied by numbers, called scalars in this context. Scalars are often taken to be real numbers, but there are also vector spaces with scalar multiplication by complex numbers, rational numbers, or generally any field. The operations of vector addition and scalar multiplication must satisfy certain requirements, called axioms, listed below. An example of a vector space is that of Euclidean vectors, which may be used to represent physical quantities such as forces. Any two forces can be added to yield a third, and the multiplication of a force vector by a real multiplier is another force vector. In the same vein, but in a more geometric sense, vectors representing displacements in the plane or in three-dimensional space also form vector spaces. Vectors in vector spaces do not necessarily have to be arrow-like objects as they appear in the mentioned examples. Vectors are best thought of as abstract mathematical objects with particular properties, which in some cases can be visualized as arrows. Vector spaces are the subject of linear algebra and are well understood from this point of view, since vector spaces are characterized by their dimension, which, roughly speaking, specifies the number of independent directions in the space. A vector space may be endowed with additional structure, such as a norm or inner product. Such spaces arise naturally in mathematical analysis, mainly in the guise of infinite-dimensional function spaces whose vectors are functions. Analytical problems call for the ability to decide whether a sequence of vectors converges to a given vector. This is accomplished by considering vector spaces with additional structure, mostly spaces endowed with a suitable topology, thus allowing the consideration of proximity and continuity issues. These topological vector spaces, in particular Banach spaces and Hilbert spaces, have a richer theory. Historically, the first ideas leading to vector spaces can be traced back as far as 17th century's analytic geometry, matrices, systems of linear equations, and Euclidean vectors. The modern, more abstract treatment, first formulated by Giuseppe Peano in 1888, encompasses more general objects than Euclidean space, but much of the theory can be seen as an extension of classical geometric ideas like lines, planes and their higher dimensional analogues. Today, vector spaces are applied throughout mathematics, science and engineering. They are the appropriate linear algebraic notion to deal with systems of linear equations. Offer a framework for Fourier expansion, which is employed in image compression routines. Or provide an environment that can be used for solution techniques for partial differential equations. Furthermore, vector spaces furnish an abstract, coordinate-free way of dealing with geometrical and physical objects such as tensors. This in turn allows the examination of local properties of manifolds by linearization techniques. Vector spaces may be generalized in several ways, leading to more advanced notions in geometry and abstract algebra. Introduction and definition. The concept of vector space will first be explained by describing two particular examples. First example, arrows in the plane. The first example of a vector space consists of arrows in a fixed plane, starting at one fixed point. This is used in physics to describe forces or velocities. Given any two such arrows, V and W, the parallelogram spanned by these two arrows contains one diagonal arrow that starts at the origin too. This new arrow is called the sum of the two arrows and is denoted V plus W. Another operation that can be done with arrows is scaling. Given any positive real number A, the arrow that has the same direction as V, but is dilated or shrunk by multiplying its length by A, is called multiplication of V by A. It is denoted AV. When A is negative, AV is defined as the arrow pointing in the opposite direction, instead. The following shows a few examples. If A equals 2, the resulting vector or has the same direction as W, but is stretched to the double length of W. Equivalently 2W is the sum W plus W. Moreover, V equals AV has the opposite direction and the same length as V. Second example, ordered pairs of numbers. A second key example of a vector space is provided by pairs of real numbers x and y. Such a pair is written as the sum of two such pairs and multiplication of a pair with a number is defined as follows: x1, y1, plus equals, and, or euro, x, y, equals. Definition: a vector space over a field F is a set of V together with two operations that satisfy the 8 axioms listed below. Elements of V are called vectors. Elements of F are called scalars. In this article, vectors are distinguished from scalars by boldface. In the two examples above, our set consists of the planar arrows with fixed starting point and of pairs of real numbers, respectively, while our field is the real numbers. The first operation, vector addition, takes any two vectors V and W and assigns to them a third vector which is commonly written as V plus W, and called the sum of these two vectors. The second operation takes any scalar A and any vector V and gives another vector of. In view of the first example, where the multiplication is done by rescaling the vector V by a scalar A, the multiplication is called scalar multiplication of V by A. To qualify as a vector space, the set of V and the operations of addition and multiplication must adhere to a number of requirements called axioms. In the list below, let U, V and W be arbitrary vectors in V, and A and B scalars in F. These axioms generalize properties of the vectors introduced in the above examples. Indeed, the result of addition of two ordered pairs does not depend on the order of the summands, xv, if, plus equals plus. Likewise, in the geometric example of vectors as arrows, V plus W equals W plus V, since the parallelogram defining the sum of the vectors is independent of the order of the vectors. All other axioms can be checked in a similar manner in both examples. Thus, by disregarding the concrete nature of the particular type of vectors, the definition incorporates these two and many more examples in one notion of vector space. Subtraction of two vectors and division by a scalar can be defined as VAW equals V plus, VA equals V. When the scalar field F is the real numbers R, the vector space is called a real vector space. When the scalar field is the complex numbers, it is called a complex vector space. These two cases are the ones used most often in engineering. The most general definition of a vector space allows scalars to be elements of any fixed field F. The notion is then known as an F-vector spaces or a vector space over F. A field is, essentially, a set of numbers possessing addition, subtraction, multiplication and division operations. For example, rational numbers also form a field. In contrast to the intuition stemming from vectors in the plane and higher dimensional cases, there is, in general vector spaces, no notion of nearness, angles or distances. To deal with such matters, particular types of vector spaces are introduced. See below. Alternative formulations and elementary consequences. The requirement that vector addition and scalar multiplication be binary operations includes a property called closure, that U plus V and R and V for all in F, and U, V in V. Some older sources mention these properties as separate axioms. In the parlance of abstract algebra, the first four axioms can be subsumed by requiring the set of vectors to be an abelian group under addition. The remaining axioms give this group an F-module structure. In other words, there is a ring homomorphism F from the field F into the endomorphism ring of the group of vectors. Then scalar multiplication of is defined as V. There are a number of direct consequences of the vector space axioms. Some of them derive from elementary group theory, applied to the additive group of vectors, for example the zero vector 0 of V and the additive inverse AV of any vector V are unique. Other properties follow from the distributive law, for example of equals 0 if and only if A equals 0 or V equals 0. History. Vector spaces stem from affine geometry, via the introduction of coordinates in the plane or three-dimensional space. Around 1636, Descartes and Fermat founded analytic geometry by equating solutions to an equation of two variables with points on a plane curve. To achieve geometric solutions without using coordinates, Bolzano introduced, in 1804, certain operations on points, lines and planes, which are predecessors of vectors. This work was made use of in the conception of barycentric coordinates by Mar paragraph Bias in 1827. The foundation of the definition of vectors was Belavita's notion of the B-point, an oriented segment one of whose ends is the origin and the other one a target. Vectors were reconsidered with the presentation of complex numbers by Argand and Hamilton and the inception of quaternions and biquaternions by the latter. They are elements in R2, R4, and R8. Treating them using linear combinations goes back to Laguerre in 1867, who also defined systems of linear equations. In 1857, Cayley introduced the matrix notation which allows for a harmonization and simplification of linear maps. Around the same time, Grassmann studied the barycentric calculus initiated by paragraph bias. He envisaged sets of abstract objects endowed with operations. In his work, the concepts of linear independence and dimension, as well as scalar products are present. Actually, Grassmann's 1844 work exceeds the framework of vector spaces, since his considering multiplication too, led him to what are today called algebras. Peano was the first to give the modern definition of vector spaces and linear maps in 1888. An important development of vector spaces is due to the construction of function spaces by Lebesgue. This was later formalized by Banach and Hilbert, around 1920. At that time, algebra and the new field of functional analysis began to interact, notably with key concepts such as spaces of P-integrable functions and Hilbert spaces. Vector spaces, including infinite-dimensional ones, then became a firmly established notion, and many mathematical branches started making use of this concept. Examples: coordinate spaces. The most simple example of a vector space over a field F is the field itself, equipped with its standard addition and multiplication. More generally, a vector space can be composed of n tuples of elements of F, such as A1, A2, An, where each I is an element of F. A vector space composed of all the n tuples of a field F is known as a coordinate space, usually denoted Fn. The case n equals 1 is the above-mentioned simplest example, in which the field F is also regarded as a vector space over itself. The case F equals and n equals 2 was discussed in the introduction above. The complex numbers and other field extensions, the set of complex numbers C, that is, numbers that can be written in the form x plus iy for real numbers x and y, whereas the imaginary unit, form a vector space over the reals with the usual addition and multiplication, plus equals plus I, y plus b, and for real numbers x, y, a, b and c. The various axioms of a vector space follow from the fact that the same rules hold for complex number arithmetic. In fact, the example of complex numbers is essentially the same to the vector space of ordered pairs of real numbers mentioned above. If we think of the complex number x plus iy as representing the ordered pair in the complex plane, then we see that the rules for sum and scalar product correspond exactly to those in the earlier example. More generally, field extensions provide another class of examples of vector spaces, particularly in algebra and algebraic number theory. A field F containing a smaller field E is an E-vector space, by the given multiplication and addition operations of F. For example, the complex numbers are a vector space over R, and the field extension is a vector space over Q. Function spaces, functions from any fixed set I copyright to a field F also form vector spaces, by performing addition and scalar multiplication pointwise. That is, the sum of two functions f and g is the function given by f plus g, w, equals f, w, plus g, w, and similarly for multiplication. Such function spaces occur in many geometric situations, when I copyright as the real line or an interval, or other subsets of R. Many notions in topology and analysis, such as continuity, integrability or differentiability, are well behaved with respect to linearity. Sums and scalar multiples of functions possessing such a property still have that property. Therefore, the set of such functions are vector spaces. They are studied in greater detail using the methods of functional analysis, see below. Algebraic constraints also yield vector spaces. The vector space f, x, is given by polynomial functions, f, x, equals rho plus r1x plus Rn a1x n a1 plus Rn xn, where the coefficients are ρ. Rn or Nf, linear equations. Systems of homogeneous linear equations are closely tied to vector spaces. For example, the solutions of are given by triples with arbitrary A, B equals A/2, and C equals a 5A/2. They form a vector space. Sums and scalar multiples of such triples still satisfy the same ratios of the three variables. Thus they are solutions too. Matrices can be used to condense multiple linear equations as above into one vector equation, namely, Ax equals 0, where A equals is the matrix containing the coefficients of the given equations, X is the vector, Ax denotes the matrix product and 0 equals is the zero vector. In a similar vein, the solutions of homogeneous linear differential equations form vector spaces. For example, phi euro squared a euro squared, x, plus 2 phi euro squared, x, plus f, x, equals 0, yields f, x, equals or euro ax plus bx a euro ax, where a and b are arbitrary constants, and x is the natural exponential function. Basis and dimension. Bases allow the introduction of coordinates as a means to represent vectors. A basis is a set B equals BII of vectors B, for convenience often indexed by some index set I, that spans the whole space and is linearly independent. Spanning the whole space means that any vector V can be expressed as a finite sum of the basis elements. Where the arc are scalars, called the coordinates of the vector V with respect to the basis B, and big elements of B linear independence means that the coordinates arc are uniquely determined for any vector in the vector space. For example, the coordinate vectors E1 equals, E2 equals, 2n equals, form a basis of Fn, called the standard basis, since any vector can be uniquely expressed as a linear combination of these vectors, x1, x2. Xn equals x1, 1, 0, 0. Plus x2, 0, 1, 0, 0, plus xn, 0, 0, 1, equals x1 e1 plus x2 e2 plus xn en. The corresponding coordinates x1, x2, xn are just the Cartesian coordinates of the vector. Every vector space has a basis. This follows from Zorn's lemma, an equivalent formulation of the axiom of choice. Given the other axioms of Zermelo-Eurofrankel set theory, the existence of bases is equivalent to the axiom of choice. The ultrafilter lemma, which is weaker than the axiom of choice, implies that all bases of a given vector space have the same number of elements, or cardinality. It is called the dimension of the vector space, denoted dim_v. If the space is spanned by finitely many vectors, the above statements can be proven without such fundamental input from set theory. The dimension of the coordinate space Fn is n, by the basis exhibited above. The dimension of the polynomial ring f, x, introduced above is countably infinite. A basis is given by 1, x, x2. A fortiori, the dimension of more general function spaces, such as the space of functions on some interval, is infinite. Under suitable regularity assumptions on the coefficients involved, the dimension of the solution space of a homogeneous ordinary differential equation equals the degree of the equation. For example, the solution space for the above equation is generated by Ax and Xax. These two functions are linearly independent over R, so the dimension of this space is 2, as is the degree of the equation. A field extension over the rationals Q can be thought of as a vector space over Q. The dimension of the field extension Q, I plus or minus over Q depends on I plus or minus. If I plus or minus satisfies some polynomial equation, Qn I plus or minus n plus Qn A1 I plus or minus Na1 plus Qo equals 0, with rational coefficients Qn. Qo I plus or minus is algebraic. The dimension is finite. More precisely, it equals the degree of the minimal polynomial having I plus or minus as a root. For example, the complex numbers C are a two-dimensional real vector space, generated by 1 in the imaginary unit I. The latter satisfies I2 plus 1 equals 0, an equation of degree 2. Thus, C is a two-dimensional vector space. If I plus or minus is not algebraic, the dimension of Q, I plus or minus over Q is infinite. For instance, for I plus or minus equals I euro there is no such equation, in other words I euro is transcendental. Linear maps and matrices. The relation of two vector spaces can be expressed by linear map or linear transformation. They are functions that reflect the vector space structure euro that is, he preserves sums and scalar multiplication, f, x plus y, equals f, x, plus f, y, and f, aax, equals aaf, x, for all x and y and v, all are in f. An isomorphism is a linear map phi via W such that there exists an inverse map gar W of V, which is a map such that the two possible compositions Fa gar W are W and Ga phi via V are identity maps. Equivalently, F is both 1-to-1 and onto. If there exists an isomorphism between V and W, the two spaces are said to be isomorphic. They are then essentially identical as vector spaces, since all identities holding in V are, via F, transported to similar ones in W, and vice versa via G. For example, the arrows in the plane, and ordered pairs of numbers vector spaces in the introduction are isomorphic. A planar arrow V departing at the origin of some coordinate system can be expressed as an ordered pair by considering the x and y component of the arrow, as shown in the image at the right. Conversely, given a pair, the arrow going by x to the right, and y up turns back the arrow V. Linear maps via W between two fixed vector spaces form a vector space on F, V, W, also denoted L, V, W. The space of linear maps from V to F is called the dual vector space, denoted var. Via the injective natural map via var, any vector space can be embedded into its bidual. The map is an isomorphism if and only if the space is finite dimensional. Once a basis of V is chosen, linear maps phi via W are completely determined by specifying the images of the basis vectors, because any element of V is expressed uniquely as a linear combination of them. If dim V equals dim W, a 1-to-1 correspondence between fixed bases of V and W gives rise to a linear map that maps any basis element of V to the corresponding basis element of W. It is an isomorphism, by its very definition. Therefore, two vector spaces are isomorphic if their dimensions agree and vice versa. Another way to express this is that any vector space is completely classified by its dimension, a single number. In particular, any n-dimensional F vector space V is isomorphic to Fn. There is, however, no canonical, or preferred isomorphism. Actually an isomorphism Fn of V is equivalent to the choice of a basis of V, by mapping the standard basis of Fn to V, via Y. The freedom of choosing a convenient basis is particularly useful in the infinite-dimensional context, see below. Matrices. Matrices are a useful notion to encode linear maps. They are written as a rectangular array of scalars as in the image at the right. Any m by n matrix A gives rise to a linear map from Fn to Fm, by the following, where denotes summation, or, using the matrix multiplication of the matrix A with the coordinate vector x, xoax. Moreover, after choosing bases of V and W, any linear map phi via W is uniquely represented by a matrix via this assignment. The determinant det of a square matrix A is a scalar that tells whether the associated map is an isomorphism or not. To be so it is sufficient and necessary that the determinant is non-zero. The linear transformation of a n corresponding to a real n by n matrix is orientation preserving if and only if its determinant is positive. Eigenvalues and eigenvectors. Endomorphisms, linear maps phi via V, are particularly important since in this case vectors V can be compared with their image under F, V. Any non-zero vector V satisfying IV equals F, V, whereas a scalar, is called an eigenvector of F with eigenvalue I. Equivalently, V is an element of the kernel of the difference Faid. If V is finite dimensional, this can be rephrased using determinants, F having eigenvalue I is equivalent to, det equals 0. By spelling out the definition of the determinant, The expression on the left-hand side can be seen to be a polynomial function in I, called the characteristic polynomial of f. If the field f is large enough to contain a zero of this polynomial, any linear map has at least one eigenvector. The vector space V may or may not possess any eigenbasis, a basis consisting of eigenvectors. This phenomenon is governed by the Jordan canonical form of the map. The set of all eigenvectors corresponding to a particular eigenvalue of f forms a vector space known as the eigenspace corresponding to the eigenvalue in question. To achieve the spectral theorem, the corresponding statement in the infinite-dimensional case, the machinery of functional analysis is needed, see below. Basic constructions. In addition to the above concrete examples, there are a number of standard linear algebraic constructions that yield vector spaces related to given ones. In addition to the definitions given below, they are also characterized by universal properties, which determine an object X by specifying the linear maps from X to any other vector space. Subspaces and quotient spaces. A non-empty subset W of a vector space V that is closed under addition and scalar multiplication is called a subspace of V. Subspaces of V are vector spaces in their own right. The intersection of all subspaces containing a given set S of vectors is called its span, and is the smallest subspace of V containing the set S expressed in terms of elements. The span is the subspace consisting of all the linear combinations of elements of S. The counterpart to subspaces are quotient vector spaces. Given any subspace W(V), the quotient space VW is defined as follows: as a set, it consists of V plus W equals V plus W, W or W, where V is an arbitrary vector in V. The sum of two such elements V1 plus W and V2 plus W is plus W, and scalar multiplication is given by AA equals plus W. The key point in this definition is that V1 plus W equals V2 plus W if and only if the difference of V1 and V2 lies in W. This way, the quotient space forgets information that is contained in the subspace W. The kernel Ker, F, of a linear map phi via W consists of vectors V that are mapped to 0 in W. Both kernel and image Im, F, equals F, V, via V are subspaces of V and W, respectively. The existence of kernels and images is part of the statement that the category of vector spaces is an abelian category, that is a corpus of mathematical objects and structure-preserving maps between them that behaves much like the category of abelian groups. Because of this, many statements such as the first isomorphism theorem, V/Ker, F, A permel Im, F, and the second and third isomorphism theorem can be formulated and proven in a way very similar to the corresponding statements for groups. An important example is the kernel of a linear map XOAX for some fixed matrix A, as above. The kernel of this map is the subspace of vectors X such that X equals 0, which is precisely the set of solutions to the system of homogeneous linear equations belonging to A. This concept also extends to linear differential equations, where the coefficients I are functions in X2. In the corresponding map, the derivatives of the function f appear linearly too, for example. Since differentiation is a linear procedure, a euro squared equals phi euro squared plus gar euro a euro squared and a euro squared equals car phi euro squared for a constant c, this assignment is linear, called a linear differential operator. In particular, the solutions to the differential equation d, f, equals 0 form a vector space. Direct product and direct sum. The direct product of vector spaces and the direct sum of vector spaces are two ways of combining an indexed family of vector spaces into a new vector space. The direct product of a family of vector spaces Vi consists of the set of all tuples I, which specify for each index I in some index set I an element Vi of Vi. Addition and scalar multiplication is performed componentwise. A variant of this construction is the direct sum, where only tuples with finitely many non-zero vectors are allowed. If the index set I is finite, the two constructions agree, but in general they are different. Tensor product. The tensor product V(Fw), or simply V(W), of two vector spaces V and W is one of the central notions of multilinear algebra, which deals with extending notions such as linear maps to several variables. A map G via W or X is called bilinear if G is linear in both variables V and W. That is to say, for fixed W the map VAG, V, W, is linear in the sense above, and likewise for fixed V. The tensor product is a particular vector space that is a universal recipient of bilinear maps G, as follows. It is defined as the vector space consisting of finite sums of symbols called tensors, V1 W1 plus V2 W2 plus Vn Wn, subject to the rules, AA equals W equals V where A is a scalar, V1 plus V2 W equals V1 W plus V2 W, and V equals V W1 plus V W2. These rules ensure that the map F from the via W to V W that maps a tuple to V W is bilinear. The universality states that given any vector space X and any bilinear map G via W and X, there exists a unique map U, shown in the diagram with a dotted arrow, whose composition with F equals G, U, V W, equals G, V, W. This is called the universal property of the tensor product, an instance of the method much used in advanced abstract algebra to indirectly define objects by specifying maps from or to this object. Vector spaces with additional structure. From the point of view of linear algebra, vector spaces are completely understood insofar as any vector space is characterized, up to isomorphism, by its dimension. However, vector spaces per se do not offer a framework to deal with the question crucial to analyze as whether a sequence of functions converges to another function. Likewise, linear algebra is not adapted to deal with infinite series, since the addition operation allows only finitely many terms to be added. Therefore, the needs of functional analysis require considering additional structures. Much the same way the axiomatic treatment of vector spaces reveals their essential algebraic features, studying vector spaces with additional data abstractly turns out to be advantageous too. A first example of an additional datum is an order of per-mille currency, a token by which vectors can be compared. For example, n-dimensional real space Rn can be ordered by comparing its vectors componentwise. Ordered vector spaces, for example Rice spaces, are fundamental to Lebesgue integration, which relies on the ability to express a function as a difference of two positive functions, f equals f plus a far, where f plus denotes the positive part of f and far the negative part. Norm vector spaces and inner product spaces. Measuring vectors is done by specifying a norm, a datum which measures lengths of vectors, or by an inner product, which measures angles between vectors. Norms and inner products are denoted and, respectively. The datum of an inner product entails that lengths of vectors can be defined too, by defining the associated norm. Vector spaces endowed with such data are known as norm vector spaces and inner product spaces, respectively. Coordinate space Fn can be equipped with the standard dot product. In R2, this reflects the common notion of the angle between two vectors x and y, by the law of cosines. Because of this, two vectors satisfying are called orthogonal. An important variant of the standard dot product is used in Minkowski space, R4 endowed with a Lorentz product. In contrast to the standard dot product, it is not positive definite, also takes negative values, for example for x equals. Singling out the fourth coordinate corresponding to time, as opposed to three space dimensions makes it useful for the mathematical treatment of special relativity. Topological vector spaces. Convergence questions are treated by considering vector spaces V carrying a compatible topology, a structure that allows one to talk about elements being close to each other. Compatible here means that addition and scalar multiplication have to be continuous maps. Roughly, if x and y and v, and a in f vary by a bounded amount, then so do x plus y and x. To make sense of specifying the amount a scalar changes, the field f also has to carry a topology in this context. A common choice are the reals or the complex numbers. In such topological vector spaces one can consider series of vectors. The infinite sum denotes the limit of the corresponding finite partial sums of the sequence A(n) of elements of V. For example, the phi could be functions belonging to some function space V, in which case the series is a function series. The mode of convergence of the series depends on the topology imposed on the function space. In such cases, pointwise convergence and uniform convergence are two prominent examples. A way to ensure the existence of limits of certain infinite series is to restrict attention to spaces where any Cauchy sequence has a limit. Such a vector space is called complete. Roughly, a vector space is complete provided that it contains all necessary limits. For example, the vector space of polynomials on the unit interval, 0, 1, equipped with a topology of uniform convergence is not complete because any continuous function on 0, 1, can be uniformly approximated by a sequence of polynomials, by the Weierstrass approximation theorem. In contrast, the space of all continuous functions on 0, 1, with the same topology is complete. A norm gives rise to a topology by defining that a sequence of vectors Vn converges to V if and only if. Banach and Hilbert spaces are complete topological vector spaces whose topologies are given, respectively, by a norm and an inner product. Their study a key piece of functional analysis focuses on infinite-dimensional vector spaces, since all norms on finite-dimensional topological vector spaces give rise to the same notion of convergence. The image at the right shows the equivalence of the one norm and a norm on a 2. As the unit balls enclose each other, a sequence converges to 0 in one norm if and only if it so does in the other norm. In the infinite-dimensional case, however, there will generally be inequivalent topologies, which makes the study of topological vector spaces richer than that of vector spaces without additional data. From a conceptual point of view, all notions related to topological vector spaces should match the topology. For example, instead of considering all linear maps via W, maps between topological vector spaces are required to be continuous. In particular, the dual space var consists of continuous functionals via R. The fundamental Hana-Banach theorem is concerned with separating subspaces of appropriate topological vector spaces by continuous functionals. Banach spaces. Banach spaces, introduced by Stefan Banach, are complete norm vector spaces. A first example is the vector space P consisting of infinite vectors with real entries x equals whose p norm given by, for p, a and, is finite. The topologies on the infinite-dimensional space P are inequivalent for different p. For example, a sequence of vectors xn equals, that is the first two n components are 2an, the following ones are 0, converges to the 0 vector for p equals a, but does not for p equals 1, but, more generally than sequences of real numbers, functions f, I copyright or are endowed with a norm that replaces the above sum by the Lebesgue integral. The space of integrable functions on a given domain I copyright satisfying fp, a, and equipped with this norm are called Lebesgue spaces, denoted LP, I copyright. These spaces are complete. Concretely this means that for any sequence of Lebesgue integrable functions f1, f2, with fnp, a, satisfying the condition, there exists a function f, x, belonging to the vector space LP, I copyright such that imposing boundedness conditions not only on the function, but also on its derivatives leads to Sobolev spaces. Hilbert spaces. Complete inner product spaces are known as Hilbert spaces, in honor of David Hilbert. The Hilbert space L2, I copyright, with inner product given by, where denotes the complex conjugate of G, X, is a key case. By definition, in a Hilbert space any Cauchy sequence converges to a limit. Conversely, finding a sequence of functions fn with desirable properties that approximates a given limit function, is equally crucial. Early analysis, in the guise of the Taylor approximation, established an approximation of differentiable functions f by polynomials. By the Stoner-Weierstrass theorem, every continuous function on a B can be approximated as closely as desired by a polynomial. A similar approximation technique by trigonometric functions is commonly called Fourier expansion, and is much applied in engineering, see below. More generally, and more conceptually, the theorem yields a simple description of what basic functions, or, in abstract Hilbert spaces, what basic vectors suffice to generate a Hilbert space H, in the sense that the closure of their span is the whole space. Such a set of functions is called a basis of H. Its cardinality is known as the Hilbert space dimension. Not only does the theorem exhibit suitable basis functions as sufficient for approximation purposes, but together with the Gram-Schmidt process, it enables one to construct a basis of orthogonal vectors. Such orthogonal bases are the Hilbert space generalization of the coordinate axis in finite-dimensional Euclidean space. The solutions to various differential equations can be interpreted in terms of Hilbert spaces. For example, a great many fields in physics and engineering lead to such equations, and frequently solutions with particular physical properties are used as basis functions, often orthogonal. As an example from physics, the time-dependent Schrödinger equation in quantum mechanics describes the change of physical properties in time, by means of a partial differential equation whose solutions are called wave functions. Definite values for physical properties such as energy, or momentum, correspond to eigenvalues of a certain differential operator, and the associated wave functions are called eigenstates. The spectral theorem decomposes a linear compact operator acting on functions in terms of these eigenfunctions and their eigenvalues. Algebras over fields. General vector spaces do not possess a multiplication between vectors. A vector space equipped with an additional bilinear operator defining the multiplication of two vectors is an algebra over a field. Many algebras stem from functions on some geometrical object. Since functions with values in a given field can be multiplied pointwise, these entities form algebras. The Stoner-Weierstrass theorem mentioned above, for example, relies on Banach algebras, which are both Banach spaces and algebras. Commutative algebra makes great use of rings of polynomials in one or several variables, introduced above. Their multiplication is both commutative and associative. These rings and their quotients form the basis of algebraic geometry, because they are rings of functions of algebraic geometric objects. Another crucial example are Lie algebras, which are neither commutative nor associative, but the failure to be so is limited by the constraints, x, y, equals a, y, x, and x, y, z plus, y, z, x plus, z, x, y equals 0. Examples include the vector space of n by n matrices, with x, y, equals x, y, x, the commutator of two matrices, and R3, endowed with a cross product. The tensor algebra T, V, is a formal way of adding products to any vector space V to obtain an algebra. As a vector space, it is spanned by symbols, called simple tensors, V1 V2 Vn, where the degree n varies. The multiplication is given by concatenating such symbols, imposing the distributive law under addition, and requiring that scalar multiplication commute with the tensor product much the same way as with the tensor product of two vector spaces introduced above. In general, there are no relations between V1 V2 and V2 V1. Forcing two such elements to be equal leads to the symmetric algebra, whereas forcing V1 V2 equals a V2 V1 yields the exterior algebra. When a field, F is explicitly stated, a common term used as F-algebra. Applications. Vector spaces have manifold applications as they occur in many circumstances, namely wherever functions with values in some field are involved. They provide a framework to deal with analytical and geometrical problems, or are used in the Fourier transform. This list is not exhaustive, many more applications exist, for example in optimization. The Minimax theorem of game theory stating the existence of a unique payoff when all players play optimally can be formulated and proven using vector spaces methods. representation theory fruitfully transfers the good understanding of linear algebra and vector spaces to other mathematical domains such as group theory. Distributions. A distribution is a linear map assigning a number to each test function, typically a smooth function with compact support, in a continuous way. In the above terminology, the space of distributions is the dual of the test function space. The latter space is endowed with a topology that takes into account not only f itself, but also all its higher derivatives. A standard example is the result of integrating a test function f over some domain I copyright. When I copyright equals P, the set consisting of a single point, this reduces to the Dirac distribution, denoted by I, which associates to a test function f its value with the P, I, f, equals f, P. Distributions are a powerful instrument to solve differential equations. Since all standard analytic notions such as derivatives are linear, they extend naturally to the space of distributions. Therefore, the equation in question can be transferred to a distribution space, which is bigger than the underlying function space, so that more flexible methods are available for solving the equation. For example, Green's functions and fundamental solutions are usually distributions rather than proper functions, and can then be used to find solutions of the equation with prescribed boundary conditions. The found solution can then in some cases be proven to be actually a true function, and a solution to the original equation. Fourier analysis. Resolving a periodic function into a sum of trigonometric functions forms a Fourier series, a technique much used in physics and engineering. The underlying vector space is usually the Hilbert space L2, 0, 2i euro, for which the functions sin mx and cos mx form an orthogonal basis. The Fourier expansion of an L2 function f is. The coefficient m and bm are called Fourier coefficients of f, and are calculated by the formulas. In physical terms, the function is represented as a superposition of sine waves, and the coefficients give information about the function's frequency spectrum. A complex number form of Fourier series is also commonly used. The concrete formulae above are consequences of a more general mathematical duality called Pontryagin duality. Applied to the group R, it yields the classical Fourier transform. An application in physics are reciprocal lattices, where the underlying group is a finite-dimensional real vector space endowed with the additional datum of a lattice encoding positions of atoms in crystals. Fourier series are used to solve boundary value problems in partial differential equations. In 1822, Fourier first used this technique to solve the heat equation. A discrete version of the Fourier series can be used in sampling applications where the function value is known only at a finite number of equally spaced points. In this case, the Fourier series is finite and its value is equal to the sampled values at all points. The set of coefficients is known as the discrete Fourier transform of the given sample sequence. The DFT is one of the key tools of digital signal processing, a field whose applications include radar, speech encoding, image compression. The JPEG image format is an application of the closely related discrete cosine transform. The fast Fourier transform is an algorithm for rapidly computing the discrete Fourier transform. It is used not only for calculating the Fourier coefficients but, using the convolution theorem, also for computing the convolution of two finite sequences. They in turn are applied in digital filters and as a rapid multiplication algorithm for polynomials and large integers. Differential geometry. The tangent plane to a surface at a point is naturally a vector space whose origin is identified with a point of contact. The tangent plane is the best linear approximation, or linearization, of a surface at a point. Even in a three-dimensional Euclidean space, there is typically no natural way to prescribe a basis of the tangent plane, and so it is conceived of as an abstract vector space rather than a real coordinate space. The tangent space is the generalization to higher-dimensional differentiable manifolds. Riemannian manifolds are manifolds whose tangent spaces are endowed with a suitable inner product. Derived therefrom, the Riemann curvature tensor encodes all curvatures of a manifold in one object, which finds applications in general relativity, for example, where the Einstein curvature tensor describes the matter and energy content of spacetime. The tangent space of a Lie group can be given naturally the structure of a Lie algebra and can be used to classify compact Lie groups. Generalizations, vector bundles. A vector bundle is a family of vector spaces parametrized continuously by a topological space X. More precisely, a vector bundle over X is a topological space E equipped with a continuous map, E in X, such that for every X in X, the fiber I1, X, is a vector space. The case dim V equals 1 is called a line bundle. For any vector space V, the projection X, Vx makes the product X, V into a trivial vector bundle. Vector bundles over X are required to be locally a product of X and some vector space V. For every X in X, there is a neighborhood U of X such that the restriction of I0 to I1, U, is isomorphic to the trivial bundle U, via U. Despite their locally trivial character, vector bundles may be twisted in the large, that is, the bundle need not be the trivial bundle X, V. For example, the Ma paragraph bias strip can be seen as a line bundle over the circle S1. It is, however, different from the cylinder S1 R, because the latter is orientable whereas the former is not. Properties of certain vector bundles provide information about the underlying topological space. For example, the tangent bundle consists of the collection of tangent spaces parametrized by the points of a differentiable manifold. The tangent bundle of the circle S1 is globally isomorphic to S1 R, since there is a global non-zero vector field on S1. In contrast, by the hairy-ball theorem, there is no vector field on the two-sphere S2 which is everywhere non-zero. K-theory studies the isomorphism classes of all vector bundles over some topological space. In addition to deepening topological and geometrical insight, it has purely algebraic consequences, such as the classification of finite-dimensional real division algebras, R, C, the quaternions H and the octonions. The cotangent bundle of a differentiable manifold consists, at every point of the manifold, of the dual of the tangent space, the cotangent space. Sections of that bundle are known as differential one forms. Modules. Modules are to rings what vector spaces are to fields. The very same axioms, applied to a ring are instead of a field F yield modules. The theory of modules, compared to that of vector spaces, is complicated by the presence of ring elements that do not have multiplicative inverses. For example, modules need not have bases, as the Z module Z/2Z shows. Those modules that do are known as free modules. Nevertheless, a vector space can be compactly defined as a module over a ring which is a field with the elements being called vectors. The algebro-geometric interpretation of commutative rings via their spectrum allows the development of concepts such as locally free modules, the algebraic counterpart to vector bundles. Affine and projective spaces. Roughly, affine spaces are vector spaces whose origin is not specified. More precisely, an affine space is a set with a free transitive vector space action. In particular, a vector space is an affine space over itself, by the map, via V, AA plus V. If W is a vector space, then an affine subspace is a subset of W obtained by translating a linear subspace V by a fixed vector X at W. This space is denoted by X plus V and consists of all vectors of the form X plus V for via V. An important example is the space of solutions of a system of inhomogeneous linear equations, Ax equals B, generalizing the homogeneous case B equals 0 above. The space of solutions is the affine subspace X plus V where X is a particular solution of the equation, and V is the space of solutions of the homogeneous equation. The set of one-dimensional subspaces of a fixed finite-dimensional vector space V is known as projective space. It may be used to formalize the idea of parallel lines intersecting at infinity. Grassmannians and flag manifolds generalize this by parametrizing linear subspaces of fixed dimension K and flags of subspaces, respectively. See also, vector, for a list of various kinds of vectors, notes. Footnotes. References, Algebra, Artin, Michael, Algebra, Prentice Hall, ISBN A978-0-89871-510-1. Blas, Andreas, Existence of Bases Implies the Axiom of Choice, Axiomatic Set Theory, Contemporary Mathematics 31, Providence, Rhode Island, American Mathematical Society, ppA 31 €33, MRA 763890. Brown, William A., Matrices and Vector Spaces, New York, M. Decker, ISBN A978-0-8247-8419-5. Lang, Serge, Linear Algebra, Berlin, New York, Springer Verlag, ISBN A978-0-387-96412-6. Lang, Serge, Algebra, Graduate Texts in Mathematics 211, New York, Springer Verlag, ISBN A978-0-387-95385-4, MRA 1878556. MacLean, Saunders, Algebra, ppA 193 €222, ISBN A 0-8218-1646-2. Mayer, Carl D., Matrix Analysis and Applied Linear Algebra, Siam, ISBN A978-0-89871-454-8. Roman, Stephen, Advanced Linear Algebra, Graduate Texts in Mathematics 135, Berlin, New York, Springer Verlag, ISBN A978-0-387-24766-3. Spindler, Karl-Heinz, Abstract Algebra with Applications, Volume 1, Vector Spaces and Groups, CRC, ISBN A978-0-8247-9144-5. German, van der Waerden, Bartel Lendert, Algebra, Berlin, New York, Springer Verlag, ISBN A978-3-540-56799-8. Analysis, Bourbaki, Nicholas, Topological Vector Spaces, Elements of Mathematics, Berlin, New York, Springer Verlag, ISBN A978-3-540-13627-9. Bourbaki, Nicholas, Integration I, Berlin, New York, Springer Verlag, ISBN A978-3. -540-41129-1. Braun, Martin, Differential Equations and Their Applications, An Introduction to Applied Mathematics, Berlin, New York, Springer Verlag, ISBN A978-0-387-97894-9. BSE 3, Tangent Plane, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Czekit, Gustav, Topology, Boston, Massachusetts, Academic Pressa, Dinnery, Philippe. Gzywicki, André, Mathematics for Physicists, Courier Dover Publications, ISBN A978-0-486-69193-0. Dudley, Richard M., Real Analysis and Probability, The Wadsworth and Brooks Cole Mathematics Series, Pacific Grove, California, Wadsworth and Brooks Cole Advanced Books and Software, ISBN A978-0-534-10050-6. Dunham, William, The Calculus Gallery, Princeton University Press, ISBN A978-0-691-09565-3. Evans, Lawrence C., Partial Differential Equations, Providence, Rhode Island, American Mathematical Society, ISBN A978-0-8218-0772-9. Folland, Gerald B., Fourier Analysis and Its Applications, Brooks Cole, ISBN A978-0-534-17094-3. Gaskett, Claude. Witomsky, Patrick, Fourier Analysis and Applications, filtering, numerical computation, wavelets, texts in applied mathematics, New York, Springer Verlag, ISBN A0-387-98485-2. Ifach, Emmanuel C. Jervis, Barry W., Digital Signal Processing, A Practical Approach, Harlow, Essex, England, Prentice Hall, ISBN A0-201-59619-9. Krantz, Stephen G., A Panorama of Harmonic Analysis, Caris Mathematical Monographs, Washington, D.C., Mathematical Association of America, ISBN A0-88385-031-1. Kreisig, Owen, Advanced Engineering Mathematics, New York, John Wiley & Sons, ISBN A0-471-85824-2. Kreisig, Owen, Introductory Functional Analysis with Applications. Wiley Classics Library, New York, John Wiley & Sons, ISBN A978-0-471-50459-7, MR 992618. Lang, Serge, Real Analysis, Addison Wesley, ISBN A978-0-201-14179-5. Lang, Serge, Real and Functional Analysis, Berlin, New York, Springer Verlag, ISBN A978-0-387-94001-4. Loomis, Lynn. H. An Introduction to Abstract Harmonic Analysis, Toronto, New York, London, D. Van Nostrand Company, Incorporated, PPAX plus 190. Schaefer, Helmut H. Wolf, MP, Topological Vector Spaces, Berlin, New York, Springer Verlag, ISBN A978-0-387-98726-2. Treves, Frana Section Wa, Topological Vector Spaces, Distributions and Kernels, Boston, Massachusetts, Academic Press. Historical References, French, Banach, Stéphane, Sur l'Europa Copyright Rations dans les ensembles abstraits et leur application aux copyright quotients into copyright grails, Fundamenta Mathematicae 3, ISNA 0016-2736. German, Bolzano, Bernard, Betrachtungen 1 Quartibarianage gegen Stochastische NDE der Elementargeometrie, French. Bourbaki, Nicolas, A Permil la Copyright d'Histoire des Mathematiques, Paris, Hermanna, Doria, Jean-Luc, A General Outline of the Genesis of Vector Space Theory, Historia Mathematica 22, 227 €261, doi, 10.1006/mot. 1995.1024, MRA 1347828. French, Fourier, Jean-Baptiste Joseph, Thar Copyright Analytique de la Chaleur, Chez Firmin Didot, Paris Filser, German, Grassmann, Hermann, Die Linealausdehnungslu, Ian Zweig der Mathematik, Oeganda, reprint, Hermann Grassmann. Translated by Lloyd C. Kannenberg, L.C., ed., Extension Theory, Providence, Rhode Island. American Mathematical Society, ISBN A978-0-8218-2031-5. Hamilton, William Rowan, Lectures on Quaternions, Royal Irish Academia, German, Mar Paragraph Bias, August Ferdinand, Der barycentrische Kalkulation des H1-Quartilfsmittel zur analytischen Behandlung der Geometrie, Moore, Gregory H., The Axiomatization of Linear Algebra, 1875 1940, Historia Mathematica 22, 262 €303, doi, 10.1006/mot. .1995.1025. Italian, Pino, Giuseppe, Calcolo geometrico secondo l'Ausdehnungslu D. H. Grassmann preceduto dall'operazioni della logica deduttiva, Turina. Further references, Ashcroft, Neil. Mermin, N. David, Solid State Physics, Toronto, Thomson Learning, ISBN A978-0-03-083993-1. Attiaor, Michael Francis, K-Theory, Advanced Book Classics, Addison Wesley, ISBN A978-0-201-09394-0, MRA 1043170. Bourbaki, Nicholas, Elements of Mathematics Algebra I Chapters 1-3, Berlin, New York, Springer Verlag, ISBN A978-3-540-. 64243-5. Bourbaki, Nicholas, General Topology. Chapters 1-4, Berlin, New York, Springer Verlag, ISBN A978-3-540-64241-1. Coxeter, Harold Scott MacDonald, Projective Geometry, Berlin, New York, Springer Verlag, ISBN A978-0-387-96532-1. Eisenberg, Murray. Guy, Robert, A Proof of the Hairy Ball Theorem, The American Mathematical Monthly 86, 572 €574, doi, 10.2307/2320587, JSTORA 2320587. Eosenbert, David, Commutative Algebra, Graduate Texts in Mathematics 150, Berlin, New York, Springer Verlag, ISBN A978-0-387-94269-8, MRA. 1322960. Goldray, Derek, Classic Set Theory, A Guided Independent Study, London, Chapman and Hall, ISBN A0-412-60610-0. Griffiths, David J., Introduction to Quantum Mechanics, Upper Saddle River, New Jersey, Prentice Hall, ISBN A0-13-124405-1. Halmos, Paul R., Finite Dimensional Vector Spaces, Berlin, New York, Springer Verlag, ISBN A978-0-387-90093-3. Halpern, James D., Bases in Vector Spaces and the Axiom of Choice, Proceedings of the American Mathematical Society 17, 670 €673, doi, 10.2307/2035388, JSTORA 2035388. Husemoller, Dale, Fiber Bundles, Berlin, New York, Springer Verlag, ISBN A978-0-387-94087-8. Jost, Jawan Quartera Gen, Riemannian Geometry and Geometric Analysis, Berlin, New York. Springer Verlag, ISBN A978-3-540-25907-7. Kreisig, Erwin, Differential Geometry, New York, Dover Publications, pp. Aziv Plus 352, ISBN A978-0-486-66721-8. Kreisig, Erwin, Advanced Engineering Mathematics, New York, John Wiley & Sons, ISBN A0-471-15496-2. Leuenberger, David, Optimization by Vector Space Methods, New York, John Wiley & Sons, ISBN A978-0-471-18117-0. MacLean, Saunders, Categories for the Working Mathematician, Berlin, New York, Springer Verlag, ISBN A978-387-98403-2. Missner, Charles W. Thorne, Kip. Wheeler, John Archibald, Gravitation, W. H. Freeman, ISBN A978-0-7167-0344-0. Narber, Gregory L., The Geometry of Minkowski Spacetime, New York, Dover Publications, ISBN A978-0-486-43235-9, MRA 2044239. German, Paragraph NHAGE, A. Strassen, Volker, Schnell Multiplication Großzahlen, Computing 7, 281 €292, doi, 10.1007/BF022423555, ISNA 0010-485 Zab, Spivak, Michael, A Comprehensive Introduction to Differential Geometry, Houston, Texas, Publish or Perisher, Stewart, Ian, Galois Theory, Chapman and Hall Mathematics Series, London, Chapman and Hall, ISBN A0-412-10800-3, Varadarajan, V.S., Lie Groups, Lie Algebras, and Their Representations, Prentice Hall, ISBN A. 978-0-13-535,732-3, Wallace, G.K., The JPEG Still Picture Compression Standard, IEEE Transactions on Consumer Electronics 38, XVIIA Euro XXXIV, doi, 10.1109/30.125072, ISNA 0098-3063. Weibull, Charles A., An Introduction to Homological Algebra, Cambridge Studies in Advanced Mathematics 38, Cambridge University Press, ISBN A978-0-521-55987-4, OCLCA 36131259, MRA 1269324, External links, Haswinkel, Michiel, ed., Vector Space, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, A lecture about fundamental concepts related to vector spaces, a graphical simulator for the concepts of span, linear dependency, base and dimension.